In the world of anti-aging science, senolytics have been the rising stars, those tantalizing compounds that promise to hunt down zombie cells, aka senescent cells, and sweep them out before they can wreak havoc. These cellular slackers accumulate as we age, stalling in a state of permanent arrest, yet continuing to secrete a stew of inflammatory factors that undermine tissue health. But the initial vision of senolytics as a silver bullet has hit a few speed bumps, namely the fact that not all senescent cells are bad, and perhaps more importantly, not all senescent cells are the same. Enter the era of precision senolytics, designer drugs that don't just obliterate any cell with a gray beard and a bad attitude, but instead identify, stalk, and selectively eliminate the real troublemakers, one subtype at a time. To understand how this works, let's revisit the messy diversity of senescent cells. Far from being a uniform population, these cells vary wildly in their origins: fibroblasts, epithelial cells, immune cells, their stressors, oxidative damage, telomere attrition, oncogenic signals, and their behaviors. Some are loud and inflammatory, flooding tissues with IL-6 and matrix metalloproteinases. Others are quiet but insidious, secreting fibrotic factors or even mimicking immune cells. And some actually do useful things, like helping remodel tissue after injury or playing temporary roles in development and regeneration. Blasting all of them indiscriminately is like trying to remove a wasp nest with a flamethrower in a museum. Sure, the wasps are gone, but so is half the building. This is where precision senolytics step in, and the tools enabling them are nothing short of sci-fi turned real. First, we have single-cell multiomics, a superpowered way of profiling cells based on their RNA expression, epigenetic state, surface markers, and metabolic quirks all at once. It's like having a full body scan, psychological profile, and dating history of every cell in a tissue sample. From this data, researchers can identify unique fingerprints that distinguish, say, a profibrotic senescent hepatic stellate cell from a reparative endothelial one. Armed with this intel, the next step is to design drugs that hit only the bad guys. This is where artificial intelligence has changed the game. Instead of screening thousands of molecules in wet labs with trial and error, AI models trained on massive chemical and biological datasets can now predict, synthesize, and virtually test new compounds with terrifying accuracy. These models don't just look for molecules that kill senescent cells, they look for ones that bind specific surface proteins, exploit unique metabolic dependencies, or disrupt the senescent cell's stress-adapted survival mechanisms. Some are trained to optimize for tissue penetration, minimal off-target effects, and even patient-specific expression patterns. Think James Bond gadgets, but for cells. One exciting example is the identification of BCL2 family dependencies in certain senescent cells, particularly those that rely heavily on anti-apoptotic pathways to stay alive. Drugs like navitoclax exploit this weakness, but now machine learning tools are helping refine this approach to avoid collateral damage such as unintended platelet toxicity. A new generation of AI-designed molecules is being developed to selectively bind to BCL-XL in senescent cells with particular expression profiles, like those found in idiopathic pulmonary fibrosis, but not in healthy lung tissue. And it's not just about what's inside the cell. Surface markers matter, too. Advances in spatial transcriptomics and proteomics are allowing researchers to map where specific senescent subtypes reside in tissues. If a senescent fibroblast in aged skin expresses a unique combination of CD markers and integrins and happens to sit next to blood vessels, a nanoparticle-coated senolytic could be engineered to home in, bind, and deliver a lethal payload without disrupting nearby youthful cells. In theory, this could lead to topical anti-aging creams that actually work, not by moisturizing but by selectively deleting the inflammatory culprits under your crow's feet. The most dazzling possibility: personalized senolytics. With enough omic data, say, from a skin biopsy, a fat sample, or even circulating cell-free RNA, it might be possible to generate a senescence profile for each patient. AI could then recommend or even custom design a cocktail of senolytic agents that target your specific burdensome cell types in your specific tissues with minimal side effects. Your zombie load, your prescription. Take that: generalized aging. Of course, there are hurdles. Regulatory approval for personalized, AI-generated therapies is still a legal and logistical minefield. Many senescent cells have complex survival mechanisms and may adapt or re-enter the cell cycle under pressure. And we're still learning exactly when and where to apply senolytics. Too soon, and we risk impairing healing. Too late, and the damage may already be irreversible. Still, the momentum is undeniable. What was once a blunt weapon is now being sharpened into a scalpel. And as our understanding deepens and the tech becomes more accessible, we may soon be able to clear the worst aging offenders, one misbehaving zombie at a time, without harming the peacemakers or the bystanders. Precision senolytics won't make us immortal, but they might just help us age with a bit more clarity, fewer inflammatory side effects, and hopefully a lot less fibro fatigue. Because sometimes aging gracefully means having the right assassin on speed dial.